Someone puts two photographs in front of you. Both are mostly black. Both are threaded with pale filaments that meet at bright, dense knots and wrap around round empty spaces where nothing is happening at all. One is a stained slice of a human brain, a few millimeters across. The other is a slab of the universe, 500 million light-years wide. Almost nobody can tell which is which. But here is what gets left out of that story. For 40 years we have been mapping where matter actually is. 1,000 galaxies, then 200,000, then 47 million. And every time the map improved, the structure got sharper instead of dissolving into noise. That should not happen to a random distribution. And the universe began as noise, variations of one part in 100,000, with no shape in them at all. So why does it look less random the harder we look? By the end of tonight, you will know exactly why. Get comfortable. If you enjoy having your sense of what counts as order quietly taken apart, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the word random will not mean what you assumed it meant. Now, let's slowly settle in. There is an experiment you can run on almost anyone, and it takes about 4 seconds. You show them two photographs side by side, and you do not tell them what either one is. Both pictures are mostly black. Both are threaded through with pale filaments that run in long curving lines across the frame. In both, those filaments meet each other at bright dense knots, and between the knots the threads thin out and stretch and sometimes fray into finer strands that dissolve into the dark. In both pictures there are round empty regions where nothing at all seems to be happening, and the filaments wrap around those empty regions the way roots wrap around a stone. Then you ask a simple question. Which of these is a piece of a human brain, and which one is a piece of the universe? Almost nobody gets it right reliably. Not laypeople, and not, in informal versions of this test, specialists. The image on the left might be a stained slice of human cerebellum, a few millimeters across, photographed through a microscope, showing the branching processes of neurons and the pale, dense clusters where they gather. The image on the right might be a slab cut out of a cosmological simulation, several 100 million light-years wide, showing the distribution of matter in the universe. The two objects have absolutely nothing to do with each other. They are separated by more than 27 orders of magnitude in size, which is a way of saying that if you shrank the universe down until it was the size of a brain, and then shrank that brain by the same factor, you would arrive at something far smaller than a single atom. They were built by entirely different forces. One was assembled by chemistry, over the course of a pregnancy and a childhood. The other was assembled by gravity, over 13.8 billion years, and you cannot tell them apart. Now, the easy thing to do with a fact like that is to get mystical about it. That is what happened when the comparison first went around the internet, and we are going to deal with that impulse honestly tonight, because it deserves better than a dismissal, and it also deserves better than a headline. But I want to start somewhere more careful than that, because there is a stranger fact hiding underneath this one, and it is the fact this whole night is built around. Here it is. For the last 40 years, astronomers have been making maps of where matter is in the universe. Not pictures of individual objects, maps. Actual three-dimensional charts of where the galaxies are, built by measuring the distance to each one at a time, hundreds of thousands and then millions of times over. And there is a thing that should have happened as those maps got better, and it did not happen, not once. When you sample a random distribution more finely, it should look more random. That is what randomness does under better sampling. Noise averages out. Apparent patterns that were artifacts of a small sample dissolve when the sample grows. If you flip a coin 10 times and get 7 heads, you might think you have found something. Flip it 10,000 times and the something goes away. This is one of the most reliable things in all of statistics, and it is the reason scientists distrust small samples so intensely. So when the maps of the universe started coming in, and they showed threads and walls and enormous holes, the reasonable expectation was that most of that would smooth out as the surveys got deeper. Some of it surely would. The rest was probably a trick of looking at a thin slice of a very big thing. That is not what happened. Every single time the maps improved, more galaxies, deeper coverage, better distances, less noise, the structure got sharper, the threads got more clearly defined, the empty regions got emptier and more clearly bounded, the knots got more obviously knot-like, Nearly half a century of increasing resolution has moved in one direction only, and it is the direction nobody would have bet on. The more of it we drew, the less it looked drawn by chance. That is the sentence I want to leave sitting in the middle of the room tonight, because it is not a poetic sentence. It is a description of a measurable trend in the astronomical literature, and it has an answer. There is a real explanation for why the universe looks less random the harder we look at it, and it is not that something arranged it, and it is not that it is alive, and it is not that we are inside a simulation, and it is also not nothing. It is a genuine and slightly unnerving fact about how order works, and by the end of tonight you're going to have it, plainly, in one sentence. But not yet. We are going to earn it. Because to understand why a random beginning produces a structure this organized, you first have to know what the structure actually is. Not the pretty version, the working version. It has parts, and the parts have names, and the names were chosen carefully by people who had to argue about them. It has a mass budget, and the mass budget is deeply counterintuitive. It has a history that starts before there were atoms. It has a scale at which it abruptly stops existing, and that fact is going to hurt more than you expect when we get there. And it has a family. That is the part that keeps people awake. Because the shape we are talking about, the branching, threading, knotting, void-surrounding shape, is not unique to the universe. It is not even unusual. You have it in your lungs. You have it in your blood vessels. You have it in the tissue you're using right now to follow this sentence. It is in the fungus under the forest floor, and in the delta where a river meets the sea, and in the flash of a lightning strike, and in the cracks that open in drying mud. Every one of those things was made by a different process, and they all converged on the same geometry. That could mean something profound. It could also mean something almost embarrassingly simple. The honest answer, when you go and look at the research, is closer to the second one. And the reason I find that more interesting rather than less is that the simple answer implies something about reality that is harder to sit with than any mystical version. So tonight we're going to go through it properly, in order, without rushing. We will start with the maps and how we got them, because that history is better than people realize. Then we will take the structure apart and look at its anatomy, and I will give you the numbers that make it stop being scenery. Then we will go all the way back to the beginning, to the moment when the universe had essentially no structure at all, and we will watch what it had to work with. Then we will find the single rule that turns the one into the other, and that rule is beautiful and completely without imagination. After that it gets stranger. We will look at the invisible scaffolding that most of this thing is actually made of. We will find where half the ordinary matter in the universe went missing, and where it turned up. We will meet the slime mould that drew a map of the cosmos, which is a real sentence and not a joke. We will look, in detail, at what the brain comparison actually measured and what it did not. We will widen out into every branching thing in nature and ask what they have in common, and then we will run into the wall. Because there is a scale, and it is not that large, cosmically speaking, beyond which every bit of this pattern simply stops. The universe above a certain size is featureless. That fact has a name, and the name is almost sad, and we will sit with it for a while. Then we will look at the handful of structures that appear to be too big to exist under that rule, and we will argue with ourselves about whether they are real. And then, at the end, the answer. Plain, in ordinary language, with nothing withheld. Get comfortable, and let me show you the first map anybody ever made of this thing, and why the people who made it thought their equipment was broken. For almost all of human history, the sky was a surface. That is not a metaphor about how people thought. It is a description of the actual data available. When you look up, you get two coordinates: how far around the sky an object is, and how far up. You do not get the third one. You do not get depth. Every star, every galaxy, every faint smudge is painted on the inside of the same dome as far as your eye is concerned, and the eye has no way to break the tie. A dim star nearby and a bright star far away look identical. For thousands of years, the universe was a picture with no perspective in it. Getting the third coordinate is the entire story of modern cosmology, and it is much harder than it sounds. You cannot measure your way out to a galaxy. What you can do is measure how fast it is moving away from you by looking at how much the light has been stretched toward the red end of the spectrum, and then convert that into a distance using the expansion of the universe. That measurement is called a redshift, and getting one means catching enough light from a single faint object to spread it into a spectrum and identify specific features in it. In the 1970s and early 1980s, this was slow, physical, tedious work. one galaxy at a time, sometimes one galaxy per night. So when a team at the Harvard-Smithsonian Center for Astrophysics set out to do this systematically, they were not building a map of the universe. They were building a map of a slice of it, a single thin wedge of sky, going outward with whatever galaxies they could reach. The point was to find out what the distribution looked like. The expectation, held by nearly everyone, was that it would look more or less like a fog. Galaxies scattered through space, clumping a bit here and there because gravity does that, but fundamentally a scatter, a homogeneous universe with some texture in it. In 1986, Valérie de Lapparent, Margaret Geller and John Huchra published the first slice. It contained roughly 1,100 galaxies. It did not look like a fog. It looked like foam. The galaxies were strung along thin arcs. The arcs curved around large round regions that contained essentially nothing. There was a prominent chain of galaxies running across the slice, with structures branching off it that people almost immediately started calling the stick man, because if you squinted it had a head and outstretched arms and legs. The whole thing looked drawn. I want to be precise about how unexpected this was, because it is easy to look back at a 40-year-old result and assume everyone saw it coming. They did not. The reaction inside the field included a serious period of asking whether the survey was somehow selecting galaxies in a way that manufactured the pattern. That is exactly the correct scientific reflex. When your data comes out looking like a structure, the first suspect is always your own method. So they went deeper. 3 years later, in 1989, Geller and Huchra reported something they called the Great Wall, a sheet of galaxies roughly 500 million light-years long and 300 million light-years wide, and only about 15 million light-years thick. Take a moment with those proportions. That object is nearly 40 times wider than it is deep. It is not a cloud. It is a membrane. And the survey had another feature that turned out to matter enormously. A few years earlier, in 1981, Robert Kirshner, Augustus Umler, Paul Schechter and Stephen Schechtman had found something in the direction of the constellation Boötes, a region roughly 330 million light-years across, centered about 700 million light-years from us, in which there were almost no galaxies at all. Not a thin patch, a hole. In a universe with a uniform distribution, a volume that size should contain something like 2,000 bright galaxies. The Boötes void contained something on the order of 60. So by the end of the 1980s, astronomy had two facts that pointed the same way. There are walls and there are holes. And nobody yet knew whether these were the larger structures in the universe, or whether they were simply the larger structures the surveys could see, which is a very different thing and a distinction that will come back hard in the second half of tonight. The way you settle that is more data, and more data came. The 2-degree field galaxy redshift survey, run largely from Australia through the late 1990s and completed in 2003, recorded around 220,000 galaxy redshifts. That is a 200-fold increase over the first CFA slice. This was the moment of truth for the small sample objection, because at that many objects you cannot blame the pattern on sparse sampling anymore. The pattern did not go away, it got cleaner. The filaments in the 2-degree field maps are more clearly threads, the voids are more clearly bounded, the intersections are more clearly intersections. Around the same period the Sloan Digital Sky Survey began the work that would eventually chart millions of objects, and in 2003 a group led by J. Richard Gott identified the Sloan Great Wall, a structure running roughly 1.37 billion light-years, nearly 3 times the length of the wall Geller and Huchra had found. And then, in the last 2 years, the resolution took another jump. In April of 2026, the Dark Energy Spectroscopic Instrument concluded its first planned survey. Over the course of that survey, it recorded more than 47 million galaxies and quasars, plus roughly 20 million stars, reaching across about 11 billion years of cosmic history. It is the largest high-resolution 3-dimensional map of the universe that has ever been made. It works by pointing 5,000 individual optical fibers at 5,000 individual objects at once, reconfiguring the whole array in about 2 minutes, and doing it again. It gathers in an evening what the CFA team gathered in years. I want to give that instrument its due, because the engineering is the reason the map exists and it usually goes unmentioned. Those 5,000 fibers are not aimed by hand. Each one sits on the end of a small robotic positioner, and the whole array of 5,000 robots is packed into a focal plane about 80 centimeters across. Between one observation and the next, all 5,000 move at once, each to a position accurate to a few micrometers, placing every fibre precisely on the image of a specific galaxy, whose position was determined in advance from imaging surveys. Then the telescope collects light for perhaps 20 minutes, the fibres carry it down to spectrographs, and the spectra are analysed to extract 5,000 redshifts. Then the robots reconfigure and it happens again, roughly 100,000 galaxy distances on a good night. Compare that with the situation in the early 1980s, when a redshift was a night's work for a graduate student and a survey of 1,000 galaxies was a career-defining project. The whole first CFA slice, the one that changed the field, the one with the stick man in it, represents less than a single hour of DESI. And when you increase your data rate by that kind of factor, you find out very quickly whether a pattern was real. There is nowhere for a small sample artifact to hide in 47 million objects. The pattern is real. That question is closed. What is not closed, and what the rest of tonight is about, is what the pattern means. And the reason that question is hard is that we know the answer to a related question with unusual precision. We know what the universe started with. And at almost the same time, the Euclid Space Telescope has been doing something complementary from a position about 1.5 million kilometers from Earth. Its first quick data release, in March of 2025, covered only 63 square degrees of sky and was accompanied by 34 scientific papers. One of the early structural results from that release is worth holding on to, because it turns the web from scenery into something with consequences. Elliptical galaxies sit closer to the spines of the filaments than disk galaxies do, which means where a galaxy lives inside this structure has something to do with what kind of galaxy it becomes. Euclid's first full cosmology data release is scheduled for this month, so put the whole sequence together: 1,100 galaxies, 220,000, millions, 47 million and counting, plus a space telescope specifically designed to map the invisible component. At every single one of those steps, the structure sharpened. Now, I want to be fair to the statistics here, because there is a legitimate reason a pattern can sharpen with more data. If the pattern is really there, more data reveals it better. That is not a paradox at all. That is just measurement working correctly. The point is not that something impossible happened. The point is what it implies about the starting conditions, and that is where this gets interesting, because we know the starting conditions with extraordinary precision, and there is nothing in them. We will get to that in 2 parts' time, and it is going to reframe everything. But first I want you to know what it is we have actually been mapping, because the cosmic web is one of those phrases that sounds like a description, and is actually a technical term with parts, and until you know the parts you're looking at a picture instead of an object. And the numbers attached to those parts are going to invert something you almost certainly believe about where the universe keeps its stuff. The cosmic web has 4 components, and they are defined by dimension. That is the elegant part. You can classify essentially every region of the universe by asking how many directions it has collapsed in. Start with the ones that have not collapsed at all. Those are the voids. A void is a region where matter has drained away in every direction, leaving something close to nothing behind. Voids are roughly spherical. They range from tens to hundreds of millions of light years across, and they have a property that most people find hard to accept the first time they hear it. Voids are the majority of the universe. In detailed simulations of large-scale structure, the volume fraction taken up by voids comes out at around 78%. More than 3/4 of everywhere is nothing much. Next, the regions that have collapsed in one direction. Those are the sheets, or walls. They are flat. They are the structures that the 1989 Great Wall belongs to, enormous in 2 dimensions, thin in the third. Think of the surfaces of soap bubbles pressed together in a foam. Everywhere 2 voids meet, you get a wall. Then the regions that have collapsed in 2 directions. Those are the filaments, and they are the load-bearing part of this entire structure. Where 2 walls intersect, you get a thread. Filaments are the long branching strands that give the web its name. They can run for hundreds of millions of light years, and galaxies flow along them like water in a channel. And finally, the regions that have collapsed in all 3 directions. Those are the nodes, the knots where filaments cross. Nodes are galaxy clusters, the densest environments in the universe, containing hundreds or thousands of galaxies bound together, filled with gas at tens of millions of degrees that glows in X-rays. Voids, walls, filaments, nodes. 3 dimensions of collapse, 4 kinds of place. That is the whole taxonomy, and it falls out of the physics rather than being imposed on it, which is one of the reasons cosmologists trust it. Now the numbers, because this is where the intuition breaks. I said voids are about 78% of the volume. Here is the other half of that fact. Voids contain roughly 6% of the dark matter. 6%. More than 3/4 of space holds 1/16 of the mass. Turn that around and look at the filaments. In the same analyses, filaments occupy something like 5% of the volume, 5% of everywhere. And inside that 5% sits roughly 1/4 of all the ordinary matter in the universe. The diffuse hot gas in filaments accounts for something on the order of 23 to 25% of the entire baryon budget, and something like 80% of a particular class of intergalactic gas we will come back to shortly. So the universe is not evenly loaded. It is not even close to evenly loaded. Almost all of the volume is almost empty, and almost all of the matter is crammed into a small fraction of the space, arranged in threads. Let me put that in a form you can feel. Imagine the universe as a house. You would find that 78% of the rooms are completely bare. No furniture, no fittings, nothing but air. And you would find that essentially everything the house contains has been stacked along the corridors. Not in the rooms, in the corridors, and the corridors are 5% of the floor plan. That is what the map shows. And when you know that, the picture stops looking like a decoration and starts looking like plumbing. Here is another way in, and it is the one I find most useful. The cosmic web is not a pattern that things are arranged in. It is a set of routes that things are moving along. Matter flows out of voids, because a void is a region of below-average density, and everything in it is being gravitationally pulled toward the denser surroundings. It flows into walls. Along walls it drains into filaments. Along filaments it travels into nodes. The web is a drainage system, and it has been running continuously for most of the age of the universe, and it is still running right now. Which brings us to our own address. In 2014, a team led by R. Brent Tully published a paper in Nature that redefined what a supercluster is. The old definition was based on where galaxies appear to be concentrated, which is a bit like defining a country by where the buildings are. Tully's team defined it by flow instead. They mapped the motions of thousands of galaxies, subtracted the general expansion of the universe, and looked at what was left, the velocities produced by local gravity. Then they drew the boundary the way a hydrologist draws a watershed. Everything whose flow lines converge to the same place belongs to the same structure. The structure our galaxy belongs to came out to be about 520 million light-years across, containing on the order of 100,000 large galaxies and something like 100 quadrillion times the mass of the Sun. They named it Laniakea, from Hawaiian words meaning immeasurable heaven. And here is the part that gets me. Laniakea is not held together. It is not gravitationally bound as a unit. The expansion of the universe is pulling it apart faster than its own gravity can assemble it. So this thing we live inside, our largest meaningful address, is defined by a flow that will never finish. Every galaxy in Laniakea is streaming toward a region we cannot see clearly, because our own galaxy's disk is in the way, a gravitational focus called the Great Attractor, and none of them will ever arrive. That is our neighbourhood, a watershed that never reaches the sea. Before we leave the anatomy, I want to take you into the part of it we almost never talk about, because it is the majority of the universe, and it gets treated as background. Go into a void. Pick the Bhuta's void, since it is the famous one. 330 million light-years across, centered about 700 million light-years away, discovered in 1981. In a uniformly filled universe, a sphere that size should hold something like 2,000 bright galaxies. It holds around 60. Now imagine standing on a planet orbiting a star in one of those 60 galaxies, somewhere near the middle of that emptiness, and looking up on a clear night. You would see your own galaxy. Stars, dust lanes, the band of a disk across the sky. The whole familiar arrangement. Everything inside your own system would look exactly as it looks to us. And beyond it, essentially nothing. A few faint smudges at the limit of detection, and then dark. No Andromeda hanging there as a naked-eye object. No neighbouring galaxies close enough to resolve. No local group. If you built telescopes and looked harder, you would find the far walls of your void eventually, but they would be so distant and so faint that for a very long stretch of your scientific history, the only reasonable conclusion available to you, reasoning correctly, from good data, with sound methods, would be that your galaxy is more or less the whole of creation. You would be wrong, and there would be no way to know. That thought experiment is not idle. It is the reason cosmologists take the cosmological principle seriously as an assumption rather than treating it as obvious. If where you stand determines what you can see, and what you can see determines what you conclude, then any statement about the universe as a whole carries a hidden clause, as observed from here. Astronomers have spent a century trying to work out how much of what we see is the universe, and how much is the seat. I bring this up because it is a useful corrective to hold for the rest of tonight. Everything we know about the shape of the universe, we know from where we happen to be standing. We are inside a filament, in a reasonably crowded neighbourhood, with a large galaxy close enough to see with the unaided eye. That is not typical. Most of the volume of the universe is void, and any observer in a void would draw a very different map with equally honest work. The pattern we are marvelling at tonight is the pattern visible from a good seat, and every single thing I have just described, the voids, the walls, the filaments, the nodes, the flows, Laniakea, the great attractor, is the outcome of a starting condition that contained none of it. Not a hint, not a seed of the shape, nothing. We know this, and we know it with better precision than almost anything else in physics, because we can look directly at the starting condition. It is still visible. It is the oldest light in the universe, and it falls on this planet from every direction at once, and when you measure the pattern in it, what you find is the closest thing to pure statistical nothing that nature has ever handed us. That is where we go next, and it is the beat where this whole night quietly turns over. There is a light that has been travelling since before there were atoms, and it is falling on you right now. It comes from every direction. It is not coming from any object, because when it was released there were no objects. It is the light of the entire universe. At the moment the universe first became transparent, and it has been stretched by the expansion of space until it is no longer visible light at all but microwaves, cold ones, corresponding to a temperature of 2.725 degrees above absolute zero. We call it the cosmic microwave background, and it is the single most informative thing anyone has ever measured. To understand what it is, you have to understand what the early universe was actually like, and the honest description is disappointing in a way that turns out to matter enormously. For the first roughly 380,000 years, the universe was a fog, hot, dense, and opaque. Everything in it was ionized. The electrons had too much energy to stay attached to nuclei, so matter existed as a plasma of bare nuclei and free electrons, with photons bouncing between them constantly. Light could not travel. It would move a tiny distance, hit a free electron, scatter off in a new direction, and do it again. If you had been there, you would have seen a uniform glow in every direction with no features in it, the way you see nothing but white when you're inside a cloud. Then the universe expanded and cooled enough that electrons could finally stay bound to nuclei. This happened at a temperature of around 3,000 degrees, and it is called recombination, which is a slightly odd name because nothing was recombining. It was combining for the first time. The instant the free electrons were used up, the fog cleared. Photons that had been scattering endlessly suddenly found themselves able to travel in a straight line, and most of them have been travelling in a straight line ever since. That last scattering surface is what we see when we look at the microwave background. It is a wall of light from the moment the lights came on. Now, here is what matters for tonight. The microwave background is not perfectly smooth. It has variations, places where it is a hair hotter, and places where it is a hair colder. Those variations correspond to places where the primordial fluid was slightly denser and slightly less dense, and those density variations are the seeds. Every structure in the universe today, every galaxy, every filament, every cluster, Laniakea, the great attractor, the Bhuta's void, grew from those variations. There was nothing else to grow from. So how big were they? 1 part in 100,000. That is the amplitude. If the average temperature is 2.725 Kelvin, the deviations are at the level of about 30 microkelvin. To give you a physical sense of that, if the surface of the ocean varied as little, proportionally, as the early universe did, the entire ocean would be flat to within a fraction of a millimetre everywhere on Earth. If a road surface varied that little, a road across a continent would deviate from perfectly level by about the thickness of a few sheets of paper. The early universe was, for all practical purposes, featureless, and it gets more pointed than that, because it is not just that the variations were small, it is what kind of variations they were. When cosmologists analyse the microwave background, one of the things they check is whether the pattern of hot and cold spots has any structure beyond pure randomness? This is a specific technical question with a specific technical answer. The field appears to be, as far as our measurements can determine, a Gaussian random field. I want to spend a minute on that phrase, because it is doing enormous work and it usually gets skipped. A Gaussian random field is the mathematical description of something that is as random as it is possible for a spatially varying quantity to be, subject to one constraint: how much variation there is at each size scale. That constraint is called the power spectrum, and the early universe's power spectrum is very close to a simple form, roughly the same amount of variation at every scale, tilted very slightly, exactly as inflation predicts. But once you have specified the power spectrum, you have specified everything. There is no additional information in the field. There are no motifs. There are no repeated shapes. There are no preferred locations. There is no rule saying that a hotspot here implies a hotspot there. Every feature is statistically independent of every other feature, except through that single spectrum, which means the initial conditions of the universe contained no design of any kind. Not a faint one, not a hidden one. The information content of the starting state is roughly a single curve describing how much noise there is at each scale, and nothing else. Let me put this as bluntly as I can, because it is the crack that everything else tonight widens. The pattern is not in the seed. Whatever it is that makes the cosmic web look like a nervous system, it did not come from the beginning. It was not encoded in the initial conditions and then unpacked. There was nothing to unpack. The universe started with the informational equivalent of static, a specification of how loud the static is at each frequency, and then static. And this is genuinely one of the great facts of physics, because you can hold both ends of the process in your mind at once. You can look at the microwave background, which is the input, and you can look at the DESI map, which is the output, and there is nothing in between except gravity and 13.8 billion years. This is also, incidentally, the reason cosmologists were able to predict the web before they saw it. If you know the initial conditions and you know the law, you do not need a telescope to know what will happen. You need a computer. And the moment computers were good enough, they grew a web. In 2005, the Millennium simulation followed just over 10 billion dark matter particles in a box 500 megaparsecs across, and the output looked like the surveys. Not vaguely like, statistically like. That is the strongest evidence there is that we understand what happened here, and it means the shape we are looking at is not a mystery about the past. It is a consequence. There is one more feature of the seed field worth mentioning, because it is the closest thing to a fingerprint the universe left on itself, and it is going to come back later. In the early plasma, gravity was pulling matter into the dense spots, and radiation pressure was pushing it back out. That produced actual sound, pressure waves travelling through the primordial fluid at over half the speed of light. Those waves ran outward from every density peak until recombination, at which point the pressure vanished and the waves froze in place. That means there is a characteristic distance stamped into the matter distribution, the distance a sound wave could travel before the universe went transparent. It is called the sound horizon, and it is about 150 megaparsecs, roughly 490 million light-years. You can still find that distance in the map today. Pick a galaxy at random, and you will find a slight excess probability of another galaxy about 490 million light-years away. It is a faint statistical bump, not a visible ring, but it is there in survey after survey, and it functions as a ruler laid across the whole universe. So the universe does have one built-in scale. It is the wavelength of the loudest sound it ever made, and it is the only thing in the initial conditions that could ever be called a feature. And even that is not really a feature in the sense we mean tonight. It is not a shape. It is a preferred separation, a slight statistical tendency for one galaxy to sit about 490 million light-years from another. It tells you nothing about where anything is, only about a spacing that shows up when you average over millions of pairs. You could not find it by looking at a picture. It took surveys of hundreds of thousands of galaxies before anyone could confirm it was there at all, and its detection in 2005 was a major result precisely because it is so faint. So the strongest structure written into the initial conditions of the universe is a statistical bump that requires 100,000 galaxies to see. Everything else, every thread, every wall, every knot, every hollow, has to come from what happened next. Everything else, every thread, every wall, every knot, has to come from what happened next. And what happened next is a single rule, and the rule has no imagination at all. In 1970, a Soviet physicist named Yakov Zeldovich published an approximation. Zeldovich is one of those figures whose career is difficult to summarize because it covers too much ground: nuclear physics, combustion, astrophysics, general relativity. The work I want to talk about is deceptively simple, and it explains more about the visible universe than almost anything else on the list. He asked what happens when a slightly overdense region in an expanding universe starts to collapse under its own gravity. The intuitive answer is that it falls inward toward its center and forms a ball. That is what we picture whenever we picture gravitational collapse, a cloud contracting into a sphere the way a star forms. But Zeldovich noticed that this only happens under a condition that essentially never holds. A region collapses into a sphere only if it is contracting at the same rate along all three axes. And a random region of a random density field is never symmetric like that. It is always at least slightly longer in one direction and shorter in another. It is a lumpy, irregular blob because that is what randomness produces, and an irregular region does not collapse all at once. It collapses fastest along its shortest axis. Think about what that means physically. If a region is a bit flatter in the vertical direction than the horizontal, then the vertical direction has less distance for material to cross, and the gravitational pull across it wins first. So the region pancakes. It collapses along one axis while the other two are still coming in slowly. And when it finishes collapsing along that first axis, you do not have a sphere, you have a sheet. That was the prediction. Zeldovich pancakes. Then what? The sheet keeps collapsing, but now along its second shortest axis. It draws in from two sides and becomes a thread, and the thread keeps collapsing along its last remaining axis and finally becomes a knot. Sheet, filament, node. Look back at the anatomy from the last part. Voids, walls, filaments, nodes. The exact four categories we find in the map, classified by how many directions they have collapsed in. Zeldovich derived that sequence from an approximation to the equations of motion 16 years before anyone had a survey capable of seeing it. And this is where the whole thing turns. Because the ordinary way to think about the cosmic web is that gravity built a complicated structure out of simple beginnings. That framing is almost exactly backwards. Gravity did not build something complicated. Gravity did the only thing it could do, over and over, everywhere at once, with no variation in the method whatsoever, and the accumulated result of a rule that simple is a structure that looks designed. The universe did not design this. It only had one way to fall. I want to slow down here and let you stand inside it, because this is the mechanical heart of the entire night, and it is worth feeling rather than just knowing. Put yourself somewhere in the universe about 500 million years after the beginning. There are no galaxies yet, or almost none. There is gas, mostly hydrogen and helium, and there is dark matter, and the whole thing is slightly clumpy at the level of 1 part in 100,000. You're inside a region a few million light years across that happens to be very slightly denser than the average. Nothing appears to be happening. On any human timescale, nothing is happening. But this region is losing the race with the expansion of the universe. Everywhere else is spreading out, and here, gravity is just barely winning. Over the next few 100 million years, you begin to notice a direction. Space around you is not contracting evenly. There is one axis along which things are closing in faster than the others, and it is the axis along which this region happened to be slightly thinner to begin with. There was no reason for it to be that axis. It simply was. The matter above you and the matter below you come toward you. The matter to your left and your right barely moves at all. What was a rough blob is now getting flatter, and the process accelerates because the closer the matter gets, the harder it pulls. And then the collapse along that axis completes, and you are standing inside a sheet. It stretches away from you in two directions for tens of millions of light years, and it is thin. The gas that fell into it has shocked and heated on arrival. This is a wall now, and there are walls forming everywhere, and where they intersect the density is doubled. The sheet keeps working. Along one of its two remaining directions, matter begins to slide, not falling from above anymore, flowing along the plane, draining toward a line. What forms is a thread, and now the flow is fast and directional, and you can see where it is going, because the thread runs somewhere. It runs to a knot, and in the knot, matter arrives from every direction at once, from several filaments at the same time, and this is the first place in the universe where anything gets truly crowded. Gas piles up and heats to tens of millions of degrees. Galaxies form and fall in and collide. That is the sequence. It happened everywhere, at every scale, simultaneously, and it is still happening now. And there is a detail in that sequence worth pausing on, because it explains something about the picture that otherwise looks like an accident. Notice that the collapse is nested. The same process runs at every scale at once, because the initial field had fluctuations at every scale at once. A region a few million light-years across is collapsing along its shortest axis, and inside it smaller regions are doing exactly the same thing on their own timescales, and inside those, smaller ones again. The small ones finish first, because there is less distance to cross. So structure builds from the bottom up. Small halos form early, and then merge and fall together into larger ones, all while the larger collapse is still in progress around them. This is why the web is not a single clean network, but a network with texture inside its texture. A filament is not a smooth tube. Look closely, and it is a chain of smaller concentrations strung along a common flow, each of which is itself made of smaller ones. A wall is not a flat plate. It is a sheet of threads. The hierarchy goes down until you reach the scale where gas pressure finally stops gravity from collapsing anything further, which is roughly the scale of individual galaxies. And this nesting is the direct source of one of the things we started the night with. When you look at an image of the cosmic web and it seems to have detail at every scale you look at, when zooming in reveals more structure rather than resolving into smooth blobs, that is not an artifact of the rendering. It is the initial power spectrum which had fluctuations at every scale, run through a rule that treats every scale the same way. The picture has detail everywhere because the input had loudness everywhere. Keep that in your pocket. It is going to be half of the answer. And notice what is missing from that description. There is no branching decision anywhere in it. Nothing chose to make a thread rather than a ball. Nothing selected the locations. Nothing optimized anything. The rule is, collapse fastest along the shortest axis. That is it. That is the entire creative act. The current theoretical work on this has gone further, and it is worth knowing where it stands because it sharpens the point rather than complicating it. In May of 2026, Francisco Shukitawa posted a treatment arguing that the cosmic web is best understood as the observable imprint of a folded multi-stream organization of phase space, that anisotropic collapse arises from the eigenvalues of a hierarchy of deformation tensors, and that the amplification of density is governed by the mathematics of how a smooth initial map gets stretched and folded. Underneath the terminology, it is the same insight Zeldovich had, made exact. The web is what you get when a smooth thing is folded by a rule, and the folds are where the material piles up. And that framing answers an objection that occurs to almost everyone who thinks carefully about this. So let me raise it now and then hold it, because we come back to it at the end. The objection is, doesn't this violate the second law of thermodynamics? The universe started smooth and became structured. Isn't order supposed to decrease? The short answer is no, and the reason is that gravity is peculiar. A self-gravitating system actually increases its entropy by clumping, unlike a gas in a box. But there is a subtler answer in the 2026 work, and it is the better one. Entropy depends on the level of description. The coarse-grained picture, the map, the thing we look at, can become more ordered while the full description, including the motions, becomes far more complex through folding and multi-streaming. In the picture, order. In the underlying reality, an explosion of complexity. Hold on to that. It is going to be the shape of the answer. For now, I want to leave you with the arithmetic of it, because it is genuinely modest. One rule. 13.8 billion years, a starting field with no information in it beyond a noise spectrum, and the output is a structure that a neuroscientist looking at a slice of it cannot distinguish from human tissue. But there is something I've been quietly leaving out of every description so far, and it is time to deal with it, because the structure we have been admiring is mostly made of a substance nobody has ever detected directly, and the parts of it we can actually see are a rounding error. In 1933, a Swiss astronomer named Fritz Zwicky pointed a spectrograph at the Coma cluster of galaxies and did an accounting problem. The Coma cluster is a node, one of those knots where filaments meet, containing on the order of 1,000 galaxies moving around inside it. Zwicky measured how fast they were moving. Then he did the calculation any physicist would do. For a cluster to hold together, its gravity has to be strong enough to keep its members from flying off. That gives you a required mass. He compared the required mass with the mass he could see in the form of stars. The numbers did not agree. They did not disagree slightly. The cluster needed enormously more mass than its visible contents could supply, by a factor of hundreds in his original estimate. Zwicky concluded that most of the matter in the cluster was some kind of dark matter, invisible to telescopes and detectable only by its gravity. The result was largely ignored for about 40 years. What revived it was rotation. In the 1970s, Vera Rubin and Kent Ford measured how fast stars orbit at different distances from the centers of spiral galaxies. The expectation, from the same physics that governs planets around the Sun, was that stars far from the center should orbit more slowly, because there is less mass pulling on them from inside their orbit. Mercury moves fast, Neptune moves slow, and the fall-off is predictable. Galaxies do not do that. In galaxy after galaxy, Rubin found that stars in the outskirts orbit about as fast as stars much further in. The rotation curves go flat, and they stay flat out to the visible edge of the disk and beyond. There is only one straightforward reading of that. The visible galaxy is embedded in a much larger, roughly spherical halo of unseen mass extending far past the stars. That result was harder to ignore, because it was not one peculiar cluster. It was every galaxy anyone looked at. The modern accounting is settled, and it is stark. Of the total energy content of the universe, roughly 68% is dark energy, which is the thing driving the accelerating expansion, and which is not our subject tonight. Roughly 27% is dark matter, and everything else, every atom, every star, every planet, every cloud of gas, every particle that has ever been part of anything anyone has ever touched, is under 5%. Now apply that to the structure we have been discussing. The cosmic web is a dark matter object. That is not a figure of speech. Dark matter dominates the mass, so dark matter dominates the gravity, so dark matter did the collapsing. The Zeldovich sequence, sheet, filament, node, ran in the dark matter first, because dark matter does not interact with light, and therefore was free to start collapsing early, while ordinary matter was still locked in the hot plasma being pushed around by radiation pressure. By the time ordinary matter was released at recombination, the dark matter had already begun laying down the framework. The gas then fell into structures that were already there, which means the galaxies are not the web. The galaxies are what happened to the small amount of visible material that fell into a web made of something else. Every glowing thing in every one of those survey maps is a decoration hanging on a scaffold that emits nothing, reflects nothing, and blocks nothing. I find this genuinely difficult to hold, so let me try to make it concrete. Take the most famous image in this whole field, one of those renderings of the cosmic web with the bright filaments and the dark voids. Almost every bright pixel in it corresponds to matter that makes up less than 5% of the content of the universe. If you could somehow see the actual mass, the filaments would be 5 times thicker and heavier than they look. The halos around every galaxy would balloon out to many times the size of the visible disk, and the structure would look less like a network of glowing threads and more like a solid, fibrous, mostly featureless mass with occasional sparks in it. The prettiness of the picture is a side effect of the fact that we can only see the frost on the window, and I should be honest about where the evidence for this stands, because dark matter is the part of modern cosmology that outsiders most reasonably question, and it deserves a proper answer rather than an appeal to authority. The strongest single piece of evidence is a collision. In 2006, a team including Douglas Clow published observations of a system called the Bullet Cluster, 2 galaxy clusters that had passed through each other. When clusters collide, the galaxies themselves mostly sail past one another, because galaxies are tiny compared to the space between them, but the hot gas, which is where most of the ordinary matter lives, does not sail past. Gas hits gas, it slows down, shocks, and gets left behind in the middle. So if all the mass were ordinary matter, the mass should be where the gas is, in the middle. The researchers measured where the mass actually was by using gravitational lensing, which maps mass directly by how it bends the light of background objects. The mass was not in the middle. The mass had sailed straight through with the galaxies, leaving the ordinary matter behind. The gravitational centers and the visible ordinary matter had physically separated. That is very difficult to explain by modifying gravity, because modified gravity theories tie the gravitational effect to where the ordinary matter is, and here it demonstrably is not. It is straightforward to explain if most of the mass is a substance that passes through itself and through everything else. And I want to be equally honest about what we have not achieved, because the gap is genuinely large, and it is not talked about enough outside the field. We have never detected a particle of dark matter. Not once, despite roughly 4 decades of increasingly extreme effort. The main approach is direct detection. Build an extraordinarily sensitive target, typically a tank of ultra-pure liquid xenon weighing several tons. Bury it more than a kilometre underground to shield it from cosmic rays, cool it, shield it again with water and lead, and wait for a dark matter particle from the halo we're supposedly moving through to strike a xenon nucleus and produce a tiny flash of light. These experiments are among the most sensitive instruments ever constructed. They can register single photons. They have to account for the radioactivity of their own components, of the rock around them, and of the air. They have found nothing. Generation after generation of detector has improved sensitivity by orders of magnitude and returned the same result: no signal. The favoured candidate particle for decades, a weakly interacting massive particle in a particular mass range, has had most of its plausible parameter space excluded. Attention has been shifting toward much lighter candidates, particularly the axion, and toward the possibility that dark matter interacts even more feebly than anyone hoped. So the situation is this. We have overwhelming gravitational evidence from at least 5 independent lines: galaxy rotation curves, cluster velocities, gravitational lensing, the detailed shape of the microwave background power spectrum, and the fact that structure formation simply does not work without it. That roughly 27% of the universe is something we cannot see, and we have no idea what it is, which means the honest description of the object we have been mapping all night is this: the largest structure in existence, whose shape we can predict and reproduce in simulations to high accuracy, is made overwhelmingly of a substance whose identity is unknown. We understand the pattern completely and the material not at all. So the scaffold is real. We have watched it come apart from its own decoration, and we still do not know what it is made of. Decades of increasingly sensitive detectors buried in mines and under mountains have not caught a particle of it. That is one of the largest open questions in physics, and it is not going to be settled tonight. But here is what matters for our purposes. When you look at that map, the one that looks like a brain, the one that got sharper with every survey, you are looking at the visible trace of a structure whose substance is unknown. The pattern is real, and it was made by something we cannot identify, following a rule we understand perfectly. And there is one more accounting problem in this story, and this one has a happier ending. Because for a long time we could not even find all of the ordinary matter, the 5%. Half of it was missing, not dark matter. Ordinary, known, boring atoms, unaccounted for. They turned up exactly where the web said they should be, and the way we found them involves an organism with no brain, no eyes, and no nervous system, which nonetheless drew a better map of the universe than we had. The missing baryon problem sounds like a bookkeeping error, and is actually one of the more embarrassing gaps in 20th century astronomy. Here is the setup. We know how much ordinary matter the universe contains. We know it 2 independent ways: from the microwave background, which encodes the density of ordinary matter in the pattern of its fluctuations, and from the abundances of the light elements produced in the first few minutes, which depend sensitively on how many protons and neutrons there were to work with. Both methods agree. The total is settled. So astronomers went and added up the ordinary matter they could actually find in the nearby universe. Stars, interstellar gas inside galaxies, the hot X-ray emitting gas in galaxy clusters, everything. They got about half. Half of the ordinary matter in the universe, not dark matter, not dark energy, just ordinary atoms, the kind everything you have ever touched is made of, was not where anyone could see it. And this was not a small discrepancy in a difficult measurement. It was 50% of a quantity we knew precisely. The simulations had a suggestion. If you grow a cosmic web in a computer and watch where the gas goes, most of it does not end up inside galaxies. It ends up strung along the filaments, in an enormously diffuse state, heated by the shocks of falling into temperatures between about 100,000 and 10 million degrees. That is hot enough to be almost completely ionized, and diffuse enough, we're talking about densities of a few particles per cubic meter, to emit almost no light at all. It is the worst possible combination for detection. Too hot to show up in the ways cold gas does, too thin to show up in the ways hot cluster gas does. The name for this stuff is the warm-hot intergalactic medium. Modern accounting puts the cool diffuse intergalactic gas at roughly 39% of all baryons and the warm-hot component at roughly 46%, meaning that, taken together, The overwhelming majority of the ordinary matter in the universe is not in galaxies at all. It is between them, and in the filaments specifically, which occupy only about 5% of the volume, the diffuse hot gas accounts for something like 23 to 25% of the entire baryon budget, and something on the order of 80% of all the warm hot gas there is. So the answer to where did half the atoms go is, they went into the threads. The web is not a pattern that galaxies happen to lie on. The web is where the matter is. Galaxies are the small fraction of it that got dense enough to light up. Finding it, though, required a new idea, and the new idea came from a mould. Physarum polycephalum is a slime mould. It is not a fungus, and it is not an animal, and it does not have a brain, a nervous system, or anything that could be called a cell wall boundary in the ordinary sense. A single individual is essentially one enormous cell with many nuclei, spreading as a yellow fan across damp, rotting wood. It eats bacteria and fungal spores. It has no eyes and no memory in any conventional sense, and it is famously, irritatingly good at solving network problems. The classic demonstration involves putting oat flakes on a surface in the same relative positions as the cities around Tokyo, dropping a slime mould on the flake representing Tokyo itself, and letting it forage. The mould spreads out in every direction, finds all the food, and then, this is the part that unsettles people, begins to retract the connections that are not carrying much traffic and reinforce the ones that are. What is left after a day or so is a network of tubes connecting the food sources. When researchers ran this and compared the result to the actual Tokyo rail system, the mould's network had comparable efficiency, comparable total length, and comparable fault tolerance. An organism with no nervous system reproduced the output of decades of human transport engineering. The reason it works is worth stating plainly, because it is the seed of the answer to tonight's question. The mould is not thinking. It is running a very simple local rule. Extend toward chemical gradients, thicken tubes where flow is high, let unused tubes wither, repeat everywhere at once. That rule, iterated across a whole organism, solves a global optimization problem that nobody in the mould is aware of. It is worth dwelling on that sentence because it is the hinge the entire second half of tonight turns on. Nobody in the mould is aware of it. There is no part of Physarum polycephalum that has a representation of the network it is building. There is no planning stage. There is no coordinator. There is not even a cell boundary between the parts, so you cannot say that one region instructs another. The whole thing is a single continuous body running one chemical rule at every point simultaneously. And what emerges is a solution to a problem that engineers need computers and years to approach. This kind of thing has a name, emergence, and the name has been used so loosely for so long that it has almost stopped meaning anything. So let me say what it means here, precisely and narrowly. It means that a rule applied locally, everywhere, without coordination, can produce a global structure that looks as though it were designed with the global structure in mind. The appearance of foresight is generated by the absence of it, because the rule does not have to work out the answer. It only has to be applied often enough that the answer is what is left standing. That is what the mould is doing, and it is, in a completely different medium with completely different physics, exactly what gravity is doing. Gravity has no representation of the cosmic web. There is no part of the universe that has a plan for where the filaments should run. There is only the local rule, mass attracts mass, and irregular regions collapse along their shortest axis, applied at every point in space at once, without coordination, for 13.8 billion years. And what is left standing is a network that looks engineered. Two systems, both brainless in the most literal sense, both arriving at a designed-looking network without any design step. The mould does it in a day, across a dinner plate. The universe does it over the age of everything, across 93 billion light-years. They are the same trick. And once you have seen that trick clearly, you start noticing that it is the only trick anyone has ever found for making complicated things. Nothing in nature builds a complex structure by planning it. Not one thing. Crystals do not plan, snowflakes do not plan, and no two are alike for the same reason that no two filaments are alike. The local conditions along the growth path differ, while the rule that responds to them does not. Embryos do not plan. A developing body is cells running local chemical rules in response to their neighbours, and the astonishing thing about development is not that a plan is executed, but that there is no plan anywhere, only gradients and thresholds. Termite mounds, with their ventilation shafts and their temperature regulation, are built by insects that hold no image of the mound. Every complicated thing you have ever seen, without exception, is a local rule applied a very large number of times. The universe is simply the largest instance of it. And the reason its output looks designed is the same reason the mold's network looks designed, and the mound looks designed, and your circulatory system looks designed. Because rules applied everywhere for long enough produce exactly what a designer would have had to work very hard to produce, and they do it without working at all. Now put that next to what we have been saying about gravity. In 2020, a team at the University of California, Santa Cruz made the connection literal. Joseph Burchett, an astronomer, had been looking for a way to trace the filaments of the cosmic web from the galaxies we can see. Oscar Elek, a researcher in computational media, suggested using a slime mold algorithm. Burchett, by his own account, was skeptical. It is a genuinely strange suggestion, one of those ideas that sounds like a joke until somebody runs it. Elek and a collaborator took a two-dimensional Fizerum model that had been developed years earlier, extended it into 3 dimensions, and modified it into something they called the Monte Carlo Fizerum machine. Here is the moment I want to put you inside. They needed to know whether the thing worked before they pointed it at real data, so they tested it against a universe they already understood. They took the Bolshoi-Planck cosmological simulation, a full gravitational simulation of structure formation, and pulled out a catalogue of 450,000 dark matter halos, just the halos, just points in space with masses attached, no filaments, no structure, no information about what connects to what, the kind of catalogue you get from a survey. Then they let the mold algorithm loose on it. The virtual agents spread outward from the halos in every direction. They sense a density field and move up its gradient. Where many agents follow the same route, the route strengthens and attracts more. Where few agents pass, the trail decays. And across the box, over many iterations, threads begin to appear between the halos, not drawn by anyone, not planned, just the accumulated preference of an enormous number of agents, each following one local rule. Then they compared the mold's output to the actual density field of the simulation, the one they had thrown away, the one the algorithm had never been shown. The fit was, in the team's own description, almost perfect. An algorithm abstracted from the foraging behavior of a brainless organism, given nothing but a list of points, had reconstructed the gravitational structure of a simulated universe. And then they did the harder thing. They took 37,662 real galaxies from the Sloan Digital Sky Survey and ran the same procedure to predict where the filaments should be in the actual universe. Then they went looking for the gas. The way you look for the warm-hot intergalactic medium is indirect and rather beautiful. You find a quasar, an extremely bright object far behind the region you care about, and you take its spectrum with an ultraviolet instrument on the Hubble Space Telescope. As the quasar's light crosses the intervening universe, any gas it passes through absorbs specific wavelengths, leaving dark lines in the spectrum. You cannot see the gas. You can see its shadow on somebody else's light. They checked those spectra against the mold's predictions. Where the algorithm said there should be a filament, the absorption was there. Where the algorithm said there should be a void, it was not. The strength of the absorption tracked the density the mold had predicted, and it fell away in the empty regions exactly as it should. A slime mold algorithm had told astronomers where to find the missing matter of the universe, and it was right. Now, it would be easy to tell that story as a curiosity, a fun fact about an unlikely method. I want to insist that it is not a curiosity. It is a data point about the thing we're actually investigating tonight, because think about what the success of that algorithm implies. The mold rule and the gravity rule are not the same rule. Gravity has no chemical gradients, no reinforcement of used pathways, no decay of unused ones. Slime mold foraging has nothing to do with mass or space-time. These are entirely unrelated physical processes, and they produce the same network, not a vaguely similar network, a network close enough that one can be used to reconstruct the other, to high accuracy from sparse data. That is not a coincidence in the sense of a fluke. That is a coincidence in the older and more interesting sense. Two things arriving at the same place from different directions, and it starts to suggest that what we are looking at when we look at the cosmic web is not really a fact about gravity at all. It might be a fact about networks, about what any system does when it has to connect points across a volume. Which brings us to the comparison that made all of this famous, and to the point in the night where the strangeness peaks. Let me step back for a moment and restack what we have. because we are about halfway through and the pieces are worth seeing together before we add the next one. We have a universe that began as close to featureless as anything can be, with density variations of 1 part in 100,000, distributed as a Gaussian random field, which is a technical way of saying noise with a specified loudness and nothing else. We have one rule, gravity, which collapses irregular regions along their shortest axis first, producing sheets, then filaments, then knots, with no alternatives available. We have 13.8 billion years of that rule running everywhere at once. We have an output in which 78% of the volume is nearly empty, and the great majority of the matter is strung along threads occupying about 5% of space. We have established that the structure is mostly made of something we cannot see and cannot identify, and we have just watched an algorithm derived from a brainless organism reproduce that structure from a list of points. And we have a question we have not answered, which is why the whole thing looks less random the more carefully we map it. Now, the comparison. In November of 2020, 2 researchers published a paper in Frontiers in Physics titled The Quantitative Comparison Between the Neuronal Network and the Cosmic Web. One of them was Franco Vazza, an astrophysicist at the University of Bologna. The other was Alberto Folletti, a neurosurgeon. That pairing is the first thing worth noticing. This was not an astronomer speculating about brains, or a neuroscientist speculating about space. It was one of each, with access to real data from both sides deciding to check. The observation they started from is the one we opened with. People had been noticing for years that images of the cosmic web and images of neuronal tissue look uncannily alike, and everyone treated it as a pleasant visual accident, because that is the sensible default. Human beings see faces in clouds. We are the least reliable pattern detectors imaginable, and the appropriate response to these 2 pictures look similar is almost always yes, and so do a great many things. So they measured it instead. The main analysis is a comparison of fluctuation spectra. In plain terms, for each system, you ask how much variation in density there is at each size scale, and you plot that as a curve. It is the same kind of analysis cosmologists run on the microwave background. It captures the statistical texture of a structure independently of its overall size, which is precisely what you need if you want to compare 2 things that are wildly different in scale. They ran it on sections of human cerebellum across the range from 1 micrometre to about 1/10 of a millimetre, and they ran it on the cosmic web across the range from roughly 5 million to 500 million light-years. The curves follow the same progression. Let me be careful about what that does and does not say, because this is exactly the point where popular coverage went off the rails. It does not say the 2 systems are the same size, obviously. The scale gap is more than 27 orders of magnitude. Written out, that is a factor of more than 1,000 trillion. If you shrank the cosmic web until its filaments were the width of neurons, and then shrank a neuron by the same factor, you would end up with something enormously smaller than a proton. It does not say the 2 systems work the same way. Neurons signal, they fire, they have thresholds, they strengthen and weaken their connections in response to use, they run on a metabolism. Filaments do none of that. There is no signal in a filament. There is no state change. There is nothing that corresponds to a synapse. And it does not say that the universe thinks, which is what a large number of headlines said. The authors have been repeatedly and publicly clear on this point. What it says is that the statistical organization of the 2 networks, how their density varies across scales, and how connected their nodes are, lands in a similar regime, and that this similarity survived being measured rather than eyeballed. The paper goes further into network properties. It looks at the degree of connectivity, meaning how many links the typical node has, and finds the 2 systems land in comparable ranges. It compares clustering, and in a section that generated most of the excitement, it estimates something like a memory capacity for each network, how much information the arrangement itself could in principle hold, and again finds the 2 systems are not wildly separated. The conclusion the authors actually drew is worth quoting in spirit, if not in exact words. It is this: despite the scale difference, and despite the completely unrelated physics governing each, diverse physical processes can build structures characterized by similar levels of complexity and self-organization. The connectivity in the 2 networks likely evolves following similar physical principles. Similar physical principles. Not the same substance, not the same forces, not the same purpose. The same principles of network construction. There is a comparison in the paper that gets less attention than the fluctuation curves, and I find it the most interesting one, so let me put it in front of you. The authors looked at connectivity, the number of connections the typical node has. In a network, this is one of the most basic descriptors you can compute, and it tends to be characteristic. Social networks have a signature, power grids have a different one, transport networks have another. The cosmic web and the neuronal network land in comparable ranges. Nodes in each tend to have a similar number of links, and the distribution of those numbers has a similar shape. This matters more than the visual resemblance does, because connectivity is a structural property that does not care what the network looks like in a photograph. Two networks can look completely different and have the same connectivity statistics, or look identical and have quite different ones. That these two agree on the boring quantitative measure, as well as the obvious visual one, is what makes the result hold together. They also worked out an estimate of how much information the arrangement of each network could in principle store. A memory capacity, in the loosest sense, meaning simply the number of distinguishable configurations the connections could take. Again, the two systems land closer than the 27 order of magnitude gap would suggest. Now, I want to fence that result carefully. A memory capacity in this sense is not memory. It is a counting exercise about configurations. The cosmic web does not store anything, cannot retrieve anything, and has no mechanism by which a configuration could be read. Calling it memory capacity is a technical convenience, and it is the phrase that did most of the damage in the popular coverage. But the structural point stands, and it is the point. Two networks built by unrelated forces across an enormous scale gap have comparable connectivity, comparable clustering, comparable fluctuation statistics, and comparable configurational richness. That is not a resemblance, that is a match. Now let me tell you what I find genuinely difficult about this, and it is not the mysticism. It is that the instrument matches the object. You are using a network to understand this. Right now, following this sentence, there is a physical structure inside your skull doing the work. Roughly 86 billion neurons with something on the order of 100 trillion connections between them, arranged in exactly the branching, knotting, void-surrounding geometry we have spent the last hour describing. And the thing that structure is currently trying to understand is another network with, by some estimates, a comparable number of galaxies in the observable universe arranged in the same way. Two networks, roughly comparable node counts, for wildly different reasons, nearly identical statistical geometry, separated by more than 27 orders of magnitude and by every possible difference in mechanism. And the smaller one is looking at the larger one and recognizing something. I want to be careful not to oversell that, because it is exactly the kind of sentence that gets turned into something silly. There is no evidence whatsoever that this matters. There is no mechanism by which the resemblance could mean anything. Nothing in physics requires the shape of the observer to relate to the shape of the observed, but it happened, and somebody checked and put a number on it, and the number held. That is the difference between a metaphor and a fact you have to carry. A metaphor you can put down. This one was measured, and it is going to sit in the room for the rest of the night. And here is where the deflation begins. Because the honest way out of this is not to make the resemblance smaller, it is to make it much, much bigger. Look at the back of your hand. If the light is right and your skin is fair enough, you can see the veins. Follow one toward your wrist and you will find it joins another, and that one joins another, and the trunk they form disappears under the muscle. Follow the same vessel in the other direction and it divides, and divides again, and the branches get finer until you cannot see them anymore, and they keep going long past that, down to capillaries a single red blood cell wide, threading every cubic millimetre of the tissue. That is a network with nodes, filaments, and a branching hierarchy. It fills a volume. It has voids in it, in the sense of regions that no vessel occupies, because a network that filled every point would leave no room for the tissue it is supposed to serve. You have another one in your chest. The airways of your lungs start with a single trunk and divide roughly 23 times, ending in hundreds of millions of tiny sacs, and the total surface area of that structure is somewhere in the range of a tennis court, folded into your rib cage. You have another in the tissue we discussed in the last part. Now step outside. Under the forest floor, fungal mycelium threads through the soil in a branching network that can extend for kilometres, connecting the roots of different trees, moving nutrients and chemical signals between them along the thickest and most used paths. A river system does it in reverse, thousands of small channels converging into fewer larger ones, and then, at the delta, dividing again into a fan of distributaries. Lightning does it in a fraction of a second. The stepped leader descends from the cloud, branching repeatedly as it probes for the path of least resistance, and what you see in a photograph is a tree. Run enough current through an insulating block, and you get the same figure burned permanently into the material, a Lichtenberg figure, branching outward from the point of discharge. Dry a bed of mud, and it cracks into a network of polygons separated by lines that meet at junctions. Freeze water on a window, and the frost grows in feathered branches. Every one of those was made by a different process. Blood vessels are grown by cells following chemical signaling gradients over months. Lightning is an electrical breakdown in air over microseconds. River deltas are carved by sediment transport over millennia. Mud cracks are a mechanical stress relief in a drying solid. Mycelium is an organism foraging. The cosmic web is gravity acting on dark matter over 13.8 billion years. They all look like each other, and two of them, as we have now seen, look like each other well enough to survive quantitative comparison. So what is actually going on? The mainstream answer is not mystical, and I think it is more interesting than the mystical answer, though it takes a moment to feel that way. The answer is that three-dimensional space is stingy. There are not many good ways to connect a lot of points across a volume, and if you have any kind of cost, energy, material, time, resistance, then the number of good ways drops to approximately one family of solutions. And every process I just listed has a cost. Take the vascular case, because it is the best studied. In 1926, a physiologist named Cecil Murray worked out what the optimal branching of a blood vessel should be if the body is trying to minimize the total cost of pumping blood plus the metabolic cost of maintaining the blood itself. The result, now called Murray's law, is a specific relationship between the radius of a parent vessel and the radii of its daughters. The cube of the parent's radius equals the sum of the cubes of the daughters, and when people go and measure actual circulatory systems, in humans and in other animals, the vessels obey it closely. The same relationship shows up in plant xylem and in insect tracheae. Nobody told the blood vessels. There is no gene encoding Murray's law. The vessels grow according to local rules, respond to shear stress, respond to oxygen demand, and the local rules find the global optimum because the optimum is the only stable place to land. And Murray's law is not an isolated curiosity. It is one member of a family of scaling relationships that show up wherever a network has to service a volume, and the family is broad enough to be slightly alarming. The same mathematics, with different exponents, depending on what is being transported and under what constraint, describes the branching of tree canopies and root systems, the airways of lungs, the vascular systems of essentially every large organism, the branching river systems of continents, and the distribution networks that human engineers designed deliberately. In the 1990s, a group of researchers proposed that this shared branching geometry is the reason for one of biology's most durable empirical regularities, that an animal's metabolic rate scales with its body mass raised to roughly the 3/4 power, across an enormous range of sizes from bacteria to whales. Their argument was that metabolism is limited by how efficiently a branching network can deliver resources to every cell in a three-dimensional body, and that the optimal such network has a specific geometry, and the exponent falls out of the geometry. That proposal has been argued about for 30 years, and the details remain contested, but the underlying observation is not contested at all. Across wildly unrelated systems, the same branching architecture appears, and it appears with quantitative regularities attached rather than as a vague visual family resemblance. And notice what none of these systems share. Trees and lungs and rivers and circulatory systems have no common ancestor, no common material, no common force, and in the case of rivers, no biology whatsoever. A river is not descended from anything. It did not inherit its shape. What they share is a problem. Move something across a volume cheaply. The number of good answers to that problem in 3 dimensions is very small, and everything that has ever faced it has found the same one. The same story, with different mathematics, explains lightning and Lichtenberg figures, and mineral dendrites and frost. The general framework is called diffusion-limited aggregation, and the core idea is that when growth happens preferentially wherever the growing structure sticks furthest out, you get branching, automatically, always. Any protrusion captures more of whatever is arriving, and therefore grows faster and protrudes further. Branching is the inevitable consequence of a positive feedback between shape and growth, and the cosmic web is a version of the same thing. A denser region pulls harder, so it gets denser, so it pulls harder. Anywhere the structure sticks out into the surrounding material, it captures more material. Layer the Zeldovich collapse sequence on top of that feedback, and threads are not one possible outcome. They are the only outcome. So here is the deflation, and I want to give it its full weight before I tell you why it does not actually deflate anything. The cosmic web does not look like a brain because the universe is a brain. The cosmic web looks like a brain because brains and universes and lungs and lightning and river deltas and slime molds are all solving the same geometrical problem. Get a network across a volume cheaply. And that problem has essentially one answer. The resemblance is real. The explanation is boring. Nature is not being poetic. Nature is being cheap. And I notice, when I say that, a small drop in the room. It is the feeling of a mystery being solved in a way that takes something away. I want to name that feeling, because it is going to happen again in a few minutes, much harder, and I would rather you see it coming. But sit with the deflated version for a second and look at what it actually claims. It claims that there is a specific geometry, branching, filamented, node and void, which is what complexity looks like when it is built under constraint. It claims that this geometry is not a property of biology, or of gravity, or of electricity, but of three-dimensional space and cost. And it claims that any process anywhere in the universe, working on any substance, under any forces, if it has to distribute or connect things across a volume with a limited budget, will land on it. That is not a smaller claim than the universe is a brain. That is a very large claim about the structure of possibility itself. It says that the number of ways to build a complex network is small, that reality found one of them independently in at least a dozen unrelated domains, and that the pattern in your skull and the pattern in the sky are the same pattern not by relation, but by necessity. I would rather have that than a mystical version, because that one is true. But we still have not answered the question the title asked, and there is a serious problem coming that has to be dealt with first. Because everything I have described tonight, the whole structure, the walls, the threads, the voids, the entire cathedral, turns out to have an edge, and past that edge there is nothing to look at. There is an assumption sitting underneath all of modern cosmology, and it is so basic that it is usually stated in the first 10 minutes of any course on the subject, and then never mentioned again. It is called the cosmological principle, and it says that on large enough scales the universe is homogeneous and isotropic. Homogeneous meaning the same everywhere. Isotropic meaning the same in every direction. No special places, no special directions, no center. Everything we can calculate about the universe depends on this. The equations that describe cosmic expansion, the ones that give us the age of the universe, the composition, the fate, assume it from the start. If it fails, essentially the entire framework has to be rebuilt, and notice the phrase in the middle, on large enough scales. That phrase is doing an extraordinary amount of work because obviously the universe is not homogeneous at small scales. You're sitting in a room that is denser than the space outside it by an absurd factor. The Earth is denser than the solar system than the galaxy than the local group. Every scale we have discussed tonight, filaments, walls, voids, laniakea, is a scale at which the universe is dramatically, obviously lumpy. So the cosmological principle is not a claim that the universe is smooth. It is a claim that there exists some scale above which the lumpiness averages out and the universe becomes statistically uniform. Which raises an obvious and extremely uncomfortable question. What scale? This is a measurable thing, and people have measured it. The technique involves the fractal dimension of the galaxy distribution. Let me explain that, because it is a lovely diagnostic. Pick a galaxy. Draw a sphere around it of radius r and count how many galaxies are inside. Now increase r and count again. In a genuinely uniform universe, the count should grow as the volume, that is, as r cubed. The exponent is 3, and the technical name for that exponent is the fractal dimension, usually written d2. If instead the galaxies are clustered, if galaxies preferentially sit near other galaxies, which they do, then the count grows more slowly than volume, because as you expand the sphere, you're increasingly enclosing empty regions. You get an exponent less than 3. On the scales where the cosmic web dominates, the measured value is somewhere near 2, which is roughly what you would expect for a structure made of sheets and threads, rather than a solid fill. So the question becomes, at what radius does the exponent climb to 3 and stay there? The definitive modern measurement came from the Wiggle-Z Dark Energy Survey. In 2012, Morag Scrimgeour and colleagues published an analysis using more than 200,000 blue galaxies across a large volume and 4 redshift ranges, using a method specifically designed to be more robust than earlier attempts. The result: the fractal dimension comes within 1% of 3 above radii of about 71 megaparsecs per h at redshift around 0.2, about 70 at redshift 0.4, about 81 at 0.6, and about 75 at 0.8. Convert those out of the units cosmologists use, and you land in the region of 300 million light-years. Above roughly 300 million light-years, the universe is uniform. Sit with the size of that number for a second, and then sit with how small it is. 300 million light-years sounds enormous. It is about 120 times the distance to the Andromeda Galaxy. It is more than half the width of Laniakea. Light leaving one edge of that sphere when the first dinosaurs were appearing on Earth would only just now be arriving at the other side, and it is nothing. The observable universe is about 93 billion light-years across, so the scale at which structure gives up is roughly 1/300th of the width of what we can see. If the observable universe were a football field, the largest interesting structure would be about a foot across. Harvard astronomer Robert Kirshner, the same Kirshner who was on the team that found the Bhuta's void, gave this transition a name. He called it the end of greatness. I have always found that phrase unexpectedly bleak, and I think it deserves its bleakness, because think about what the last hour has been. We have walked through the discovery of the most organised-looking structure anyone has ever found. We have looked at walls 500 million light-years long and 15 million thick. We have looked at voids so empty they should not be possible. We have looked at a network that a neurosurgeon and an astrophysicist compared quantitatively and found to hold up. We have found our own address in a watershed of galaxies streaming towards something we cannot see, and every bit of that is a surface texture on something fundamentally featureless. Zoom out past the end of greatness, and it all goes away. Not gradually, and not gracefully. The measurement is quite sharp. The filaments stop being distinguishable. The voids stop being holes and become fluctuations. The walls average into the background, and what you're left with is a uniform grey haze, the same in every direction, out to the limit of what can be seen, with no features in it at all. The universe is only beautiful at scales small enough for us to be inside. That is the emotional weight of the end of greatness, and I do not think there is a way around it. Everything we have been marvelling at tonight is local. It is a texture, and the reason it is local is not mysterious. It is that the universe has only been around for 13.8 billion years, and gravity only propagates at the speed of light, so nothing has had time to organise across a distance larger than roughly the sound horizon and its descendants. Structure requires causal contact. The universe has not been in touch with itself long enough to build anything bigger, and there is a second reason, which is subtler, and which I think makes the end of greatness less bleak once you see it. Structure at a given scale takes a certain amount of time to form, and larger structures take longer, much longer. A galaxy assembles in a few 100 million years. A cluster takes several billion. A supercluster scale flow like Laniakea has been in progress for most of the age of the universe, and as we said, has not finished and never will. So the sequence of collapse has a front edge to it. It has worked its way up from small scales, where it finished long ago, to intermediate scales, where it is finishing now, and it is currently in the middle of the largest scales it will ever reach. The homogeneity boundary is not a wall the universe ran into. It is the position of the wavefront. It is how far up the ladder of scales gravity has managed to climb in 13.8 billion years. And in an ordinary universe, one without dark energy, that boundary would keep moving outward. Structure would keep growing. Given long enough, larger and larger regions would collapse, and the end of greatness would retreat. But we do not live in that universe. The expansion is accelerating, and accelerating expansion is very effective at stopping structure formation, because it pulls apart regions that have not yet finished collapsing, which means the boundary is close to being frozen. The largest structures that will ever exist in this universe are, more or less, the ones that exist now. We are living at the moment when the cosmic web is as elaborate as it is ever going to get. That reframes the sadness a little, I think. The end of greatness is not a statement that the universe is boring. It is a statement about a construction project that has been running since the beginning, is currently at its high water mark, and is about to be stopped by the expansion of space. Everything we map tonight is the finished work. Now, I told you a few minutes ago that I would name the feeling when a mystery gets solved in a way that takes something away, and this is the second time. But there is something worth noticing about how this one lands, and it is the reason I put it here rather than at the end. The end of greatness is a constraint on the pattern, not an explanation of it. It tells you where the web stops. It does not tell you why. Below that boundary, it looks so overwhelmingly non-random. In fact, it sharpens that question rather than answering it, because now we know the phenomenon has a definite scale range, from roughly the size of a galaxy cluster up to about 300 million light-years, inside which a random starting field produced something that looks authored. And there is one more thing about the end of greatness that has to be said, and it is the reason this part is not the last word. The measurement of the homogeneity scale is a statistical statement. It says that if you average over enough directions and enough volumes, uniformity wins above 300 million light-years. It does not say that no individual structure larger than that exists. Statistics permits rare exceptions. That is what statistics is. So the obvious thing to do is go and look. And when people went and looked, they found things they cannot easily explain, and the list has been getting longer rather than shorter. Some of those things are almost certainly not real. At least one of them, if it is real, is a serious problem for the framework we have just spent this part describing. They are the largest things anyone claims to have found, and they should not be there. The first one is uncontroversial, and it is where the trouble starts politely. The Sloan Great Wall, identified in 2003 by a group including J. Richard Gott, runs about 1.37 billion light-years. That is already more than 4 times the homogeneity scale. It is real, it is well sampled, and nobody disputes its existence. The usual response is that this is fine. The Sloan Great Wall is not a bound object. It is a chance alignment of several superclusters that happen to lie along a similar direction, and statistical uniformity permits such alignments at some rate. That is a reasonable answer, and for the Sloan Great Wall specifically I think it holds. A structure 4 times the homogeneity scale is a stretch, not a rupture. Then it gets less comfortable. In 2013, Roger Close and colleagues reported a structure traced by quasars, extremely luminous objects powered by matter falling into supermassive black holes, which have the great advantage of being visible from enormous distances. They found a group of 73 quasars whose characteristic size came out around 1.2 billion light-years, and whose longest dimension was on the order of 4 billion. They called it the Huge Large Quasar Group, which is an unfortunate name for a serious result. 4 billion light-years is roughly 13 times the homogeneity scale. Then, more recently, work by Alexia Lopez and collaborators using magnesium absorption in quasar spectra has produced 2 more. In 2021 they reported the Giant Arc, a crescent of galaxies and gas on the order of 1.3 billion light-years across. In 2024 they reported the Big Ring, a nearly circular structure of comparable scale in the same general region of sky. Both are above the nominal homogeneity limit, and the fact that 2 such structures sit near each other makes the chance alignment explanation harder to run. And then there is the one that breaks the scale entirely. The Hercules Corona Borealis Great Wall was identified by Istvan Horvath, John Hakila, and Zsolt Bagoli using gamma-ray bursts as tracers. Gamma-ray bursts are the brightest explosions in the universe. For a few seconds, a single burst can outshine everything else, and because they are so bright, they can be seen from further away than almost any other object. The claimed structure has an extent on the order of 10 billion light-years. 10 billion. That is roughly 10% of the diameter of the observable universe. It is more than 30 times the homogeneity scale. I want to put you inside that number for a moment, and then I want to take it apart honestly, because both of those things are necessary and the order matters. Imagine yourself at one end of it, and imagine you can travel at the speed of light, which nothing with mass can do, but allow it. You set off along the structure's long axis. You pass the far side of our own galaxy in about 80,000 years. Andromeda takes 2.5 million. You cross the width of Laniakea, our entire home supercluster, that watershed of 100,000 galaxies, 520 million years, and you have gone 5% of the way. You keep going. The whole history of complex life on Earth passes and you are not close. 1 billion years. 2. The Earth itself did not exist when you would have needed to leave. 5 billion years in, the Sun has not yet formed behind you, and you are halfway. 10 billion years of travel at the speed of light, and the structure is still not older than the universe, but it is close enough that the comparison stops making sense. You would be travelling for roughly 3/4 of the age of everything, and the universe would have expanded substantially underneath you while you did it, which is one of the technical reasons the claim size is so awkward. Now let me undercut it, because you deserve the honest version. Gamma-ray bursts are terrible tracers of structure. They are rare. They are transient. You have to be looking when one goes off. The sample used to identify this structure was small, scattered across an enormous volume, and subject to complicated selection effects concerning which bursts get detected and which get redshifts measured. Several groups have reanalyzed the statistics and argued that the apparent clustering is not significant, that if you generate random burst distributions with realistic selection effects and look for the largest apparent grouping, you find things like this reasonably often. That is a strong objection, and it may well be correct. If I had to bet, I would bet that the Hercules Corona Borealis Great Wall as a physical structure is not real, and that what was found is a pattern in a sparse sample. But I want to be careful about how satisfied that makes me, for two reasons. The first is that the pattern is in the sampling, not the universe, is exactly what people said about the CFA slice in 1986. It was the correct default then, and it was wrong. Every increase in data since has moved in the same direction, and the trend deserves some weight. The second is that the objection only works well for the sparsest tracers. It works for gamma-ray bursts. It works less well for the quasar group, and less well again for the magnesium absorber structures, which use a much denser and better understood tracer. You cannot dismiss the whole list with one argument, and the list has grown. So where does this actually leave us? It leaves us with a genuine, live, unresolved tension in cosmology, which is worth stating plainly rather than smoothing over. On one side, we have a well-measured homogeneity scale of around 300 million light-years, confirmed by multiple surveys with careful methodology, and we have a theoretical framework that requires it, and that succeeds spectacularly at predicting almost everything else. On the other side, we have a growing catalogue of individual structures ranging from 1 to 10 billion light-years, some of which are certainly statistical flukes, some of which are probably chance alignments, and at least a few of which are becoming hard to explain away. The people who work on this are not panicking, and they should not be. The standard model of cosmology is in extremely good shape overall, but the reconciliation has not happened, and the new data now arriving is exactly the data that will decide it. DESY has 47 million objects. Euclid's first full cosmology release lands this month. Within a few years, the question of whether structures above the homogeneity scale exist will be settled one way or the other, and neither answer would be boring. If they turn out to be flukes, then the pattern really does stop at 300 million light-years, and the end of greatness is exactly what it says. And if they turn out to be real, then the ceiling is higher than we thought. The cosmological principle needs work, and the answer to tonight's question gets an extra edge on it, because it would mean the trend we started with, the one where the universe looks less random every time we improve the map, has not finished. Either way, we now have everything we need. We have the seed, and we know it was noise. We have the rule, and we know it has no options. We have the output, and we know its anatomy, its mass budget, its invisible substance, its family resemblance to every other branching thing in nature, and the scale at which it stops. So let me answer the question. The universe looks less random the more we map it because we're not looking at the randomness. We are looking at what a rule with no choices in it did to the randomness over 13.8 billion years, and the rule is the only thing in the picture. That is the answer. Let me now take it apart because it is one of those sentences that sounds thin until you see what is inside it. The mistake almost everyone makes, and I include myself for years, is to assume that randomness is a property that persists, that if you start with something random, you have something random, and it stays random, and any order that shows up later had to come from somewhere. That is not how it works. Randomness is a property of a distribution, not of an object, and it lives in the starting conditions. It says nothing about what happens next. Here is the cleanest way I know to see it. Take a bag of dry sand and pour it slowly onto a flat table. The individual grains are as random as anything gets. No grain knows about any other, none of them were arranged, and where each one lands relative to its neighbours is genuinely unpredictable in any practical sense, and what forms is a cone, every time, with a specific angle, the same angle, reproducible to within a degree or two, determined by the friction between grains. That angle is a physical constant of the material, and you can look it up. Nobody arranged the cone, nobody chose the angle. The grains are random and the shape is not, and there is no contradiction anywhere in that, because the shape is not a property of the grains, it is a property of what gravity and friction do to grains. And notice something else about the sand, because it is the piece that closes the argument. If you want to know about the individual grains, their sizes, their shapes, the particular way this batch differs from another, pouring them onto a table is the worst possible way to find out. The pile destroys that information. Everything specific about the grains gets averaged into a single number, the angle, and the angle tells you about friction rather than about any grain. But if you want to know about friction, the pile is an excellent instrument. In fact, it is a better instrument than examining the grains would be, because it integrates the behavior of millions of them into one clean measurement. So the pile is not a picture of the sand, it is a picture of the rule. That distinction is the whole thing, and it is where the intuition most people carry goes wrong. When we look at a map of the universe, we assume we are looking at the contents, at where the matter happens to be, which is a fact about the specific universe we got. And in a limited sense we are. But the reason the map has the character it has, the reason it is threaded and knotted and hollow rather than smooth or speckled or striped, has nothing to do with our particular universe's particular fluctuations. Run the whole thing again with a completely different random seed, and you would get a different map with all the same properties, different filaments in different places, the same kind of filaments, the same statistics, the same fractal dimension, the same end of greatness. The specific web is an accident. The fact that it is a web is not. And this is why the trend in the surveys was never going to reverse. Every improvement in the map has been an improvement in our measurement of the rule, and the rule is exact. There is no amount of additional data that can make an exact thing look fuzzier. Now scale that up by an unimaginable amount and remove the friction and the table. The early universe was the sand, a random field with a specified statistical loudness and no other information in it, and gravity is the pouring. And 13.8 billion years later, the cone is a cosmic web. The randomness is still there, by the way. That is the part people miss. It is in the specific locations. Why is the Bhutas void where it is and not somewhere else? Random. Why does this filament run in this direction and not another? Random. Why is our galaxy in this particular thread of Laniakea? Random. Every particular fact about where anything is a direct inheritance from a fluctuation in the primordial field that had no reason to be there. What is not random is the kind of thing that formed. Thread, wall, knot, void. Those were never in question. Those were fixed the moment the universe contained gravity and 3 spatial dimensions. So the map has 2 layers in it, and they behave completely differently. The where is noise, the what is law. And when you improve the map, you are not sampling the noise better, you are resolving the law better. The law is deterministic, so it sharpens without limit as your resolution improves. The noise never sharpens, because there is nothing in it to sharpen into. That is why the trend has run in one direction for 40 years and will keep running. Every survey since 1986 has been increasing the resolution on a deterministic structure, and deterministic structures look more structured the closer you look. There was never going to be a survey that made the web dissolve. The web is not a pattern in the data, it is the data. Let me put you inside the whole thing once, from the beginning, and then I will finish the argument, run the map backwards, take the DESI catalogue, 47 million objects, and start winding time in reverse. The galaxies begin to drift apart because expansion is running backwards and everything is coming closer together, but the structures themselves are also unbuilding. The clusters loosen. The knots at the filament intersections come undone, and their contents flow back outward along the threads they came in on, which is a strange thing to picture. Matter travelling backwards up a drain. The filaments thin. They stop being sharp lines and become ridges, and the ridges broaden. The walls lose definition and spread into thicker slabs, and then into gentle rises. The voids fill in, the emptiness draining back until the holes are only slight depressions and then only faint hints. Keep going. Now there are no galaxies at all, only gas and dark matter. Now there is no structure you could point at. The map is a haze with the faintest suggestion of texture in it, and the texture is fading. And then you arrive, 380,000 years after the beginning, at the surface where the light was released, and you look around. There is nothing here. It is uniform in every direction. It is hot and dense and featureless, and it varies from place to place by about 1 part in 100,000, a variation so small that if you were standing in it, you would have no way to detect it with any sense you possess. There are no threads, there are no walls, there is no hint of the shape that is coming, there is no plan, no template, no seed of the design, nothing that a very clever observer standing here could point at and say, that is where Laniakea will be. Nothing but noise, with a specified loudness at each scale. Now run it forward, fast. The tiny overdense regions begin to pull. Each one collapses along its shortest axis, because that is the only thing it can do. Sheets appear across the entire volume simultaneously, not one at a time, everywhere at once, because everywhere had a slightly shortest axis. The sheets intersect. Threads form along the intersections. Matter starts flowing, and every flow is downhill, and downhill means toward the nearest concentration. The threads intersect and knots form at the crossings. Gas falls in, shocks, heats, and begins to glow. The voids empty out because everything in them is being pulled toward everything around them, and after 13.8 billion years of that, with no interventions, no adjustments, and no decisions of any kind, you have a structure that a neurosurgeon looks at and recognizes. The universe did not design this. It only had one way to fall. That is the whole of it. And I said earlier there was an objection worth raising about order and entropy, and this is where we settle it, because it is the last place the mystical reading could hide. The objection goes, even if gravity is deterministic, the universe still went from a smooth state to a structured one, and the second law of thermodynamics says disorder increases. So something must have supplied the order. The first answer is that gravity is genuinely different from every other force in this respect. For a gas in a box, the highest entropy state is uniform, spread out evenly. For a self-gravitating system, the highest entropy state is clumped. Gravity has no equilibrium in the ordinary sense. A self-gravitating system left alone gets more concentrated, not less, and its entropy rises the whole time. So the formation of structure under gravity is not fighting the second law. It is the second law running. But the 2026 work I mentioned earlier gives a better answer, and it is the one I want to leave you with, because it reframes the entire question. Entropy depends on the level of description. When you look at the map, the coarse-grained picture, the density in each region, the universe has become more ordered. That is real. That is what we have been looking at all night. But the map is not the full description. The full description includes how everything is moving, and there the story is completely different. In the early universe, at any given point, matter was doing one thing, expanding at essentially one velocity, one stream. As collapse proceeds, material falls in, passes through, and comes out the other side while more material is still falling in, a process called shell crossing. Now, at a single point in space, there are two streams moving in different directions, then four, then many. The phase space of the system folds over on itself repeatedly, and the number of independent motions at each location explodes. That is what Kitara's 2026 treatment means when it describes the cosmic web as the observable imprint of a folded multi-stream organization. The filaments and nodes we see are the places where phase space has been folded most, and matter has piled up in the creases. So, order in the picture, and a combinatorial explosion of complexity in the underlying description. The apparent order and the increasing entropy are not in conflict, because they are statements about two different things. The universe got simpler to draw and enormously more complicated to be, and that, finally, is why the resolution paradox we started with was never a paradox. Better maps show more structure because the structure is the deterministic residue of a rule. Better maps would show more randomness only if we were mapping the seed, and we cannot map the seed because the seed is gone. It was consumed. Every scrap of that primordial noise was fed through the amplifier, and what came out the other side is not noise plus order. It is the shape of the amplifier itself, printed across 93 billion light-years, using noise as its ink. We have been looking at gravity's handwriting this whole time and mistaking it for a message. There is one more thing to say, and it is the thing that has been waiting since the first minute of tonight. Because if this is right, if this specific geometry is what any process produces when it distributes anything across a volume under constraint, then the resemblance we opened with is not a curiosity, and it is not mysticism, and it is also not nothing. It is a statement about how few options reality has. Let me deal with the mystical readings properly before we finish, because they deserve to be answered rather than sneered at, and because answering them is what makes the real position clear. The first and loudest is that the universe is a brain, or is conscious, or is thinking. This got attached to the Vadza and Folletti paper almost immediately. In headlines the authors did not write and did not endorse. The answer is not that the resemblance is fake. We have spent the night establishing that it is real and measured. The answer is that structure is not function. Two systems can share a network geometry and share nothing else, and in this case they share nothing else at all. A neuron fires. It has a threshold, an action potential, a refractory period, a metabolism, and connections that strengthen and weaken with use. A filament of the cosmic web has none of these. There is no signal in a filament. There is no state that changes. There is nothing that plays the role of a synapse, and without something that plays the role of a synapse there is no computation of any kind, let alone thought. The paper found similar statistics of connectivity. It did not find, and did not claim to find, anything that does anything. The second is cosmopsychism, the philosophical position, held by serious people including Philip Goff, that consciousness might be fundamental to reality, or might exist at the cosmic scale. I want to treat this differently from the headlines, because it is a real position in philosophy of mind held by people who argue for it carefully, and it exists mostly because the relationship between physical description and subjective experience is genuinely unsolved. But it is not supported by anything we looked at tonight, and its defenders would generally agree. It is a response to a problem in the philosophy of mind, not a conclusion drawn from cosmology. The cosmic web makes no prediction that could confirm or refute it. If you find cosmopsychism attractive, nothing in the fluctuation spectrum of a galaxy survey should make you more confident, and if you find it implausible, nothing there should trouble you. It is a separate conversation, and it is worth keeping separate. The third is the simulation argument, and it comes up here specifically because of the slime mold. If a simple procedural algorithm can generate the universe's structure, doesn't that suggest the universe is being generated by an algorithm? The answer is that this reverses the inference. What the slime mold result shows is that the rules producing cosmic structure are simple enough that a very different simple rule lands in the same place. But physicists have been arguing that the rules of nature are simple for 400 years. That is the entire premise of the discipline. A universe that is compressible into short rules is exactly what we expected to find, and finding it is not evidence of a compressor. A rule being simple does not imply somebody wrote it any more than the angle of a sandpile implies somebody chose it. And the fourth, which is not mystical at all but is the serious minority scientific position, is the fractal universe. Luciano Pietronero, Francesco Silos Labini, and colleagues have argued for decades that galaxy clustering remains fractal to far larger scales than the standard model allows, that the fractal dimension stays near 2 rather than climbing to 3, and therefore that the homogeneity scale we discussed does not exist in the way the surveys report it. This deserves respect, because for a period it was a real open question and the data was not good enough to settle it. But it is largely settled now. Wiggle-Z, and subsequently the Baryon Oscillation Spectroscopic Survey and others, have measured the transition to a fractal dimension of 3 with careful methodology and consistent results across independent samples and redshift ranges. What survives from the fractal program is a genuinely useful caution that shallow incomplete catalogues can manufacture apparent scaling, and that caution is now standard practice. So all 4 readings come apart, and what is left is the deflationary explanation, and I want to end by taking that explanation seriously enough to see what it actually says about you. We opened tonight with 2 pictures nobody can tell apart. At the time, that was a curiosity. It read like a coincidence, or a party trick, or at most a hint that something large was going on that we did not have a name for. We have the name now, and it is not what anyone expected. The 2 pictures look the same because there are not many ways to build a network across 3-dimensional space under constraint. Not a few thousand ways, not a few dozen. Essentially one family, with variations in the details. If you must connect a great many points, and you must move something between them, and you cannot spend unlimited material or energy or time doing it, then you will get branching. You will get hierarchy, a small number of large channels feeding a large number of small ones. You will get nodes where paths converge. You will get regions the network does not enter, because a network that entered everywhere would leave nothing for the network to serve, and the statistics of the result will look like the statistics of every other solution to the same problem, no matter what it is made of. Blood found it, lungs found it, mycelium found it, river systems found it. Lightning finds it in a fraction of a second, every time, from scratch. A single-celled organism with no nervous system finds it well enough that its algorithm can reconstruct a cosmological simulation. Neurons found it, and gravity, working on invisible matter across 93 billion light-years for 13.8 billion years, with no chemistry, no metabolism, no signaling, no purpose, and no capacity to be influenced by any of the others, found the same one. That is the finding. Not that the universe is a mind, something less comforting and considerably larger, that reality has a very small number of ways to build anything complicated, and it keeps arriving at them independently, and the pattern in your skull and the pattern in the sky are the same pattern, not because they are related, but because there was nothing else for either of them to be. You're not made in the image of the universe. The universe is not made in the image of you. Both of you are made in the image of the constraint. And I want to leave one thing genuinely open, because it is open, and because pretending otherwise would be a poor way to end a night like this. We do not know whether the pattern really stops. The end of greatness says it does. 300 million light-years and the structure averages away into uniformity. That is the measurement. It is a good measurement, and the framework built on it works. But sitting alongside it is a list of things that should not exist. A wall of 1.3 billion light-years, a quasar group of 4 billion, a ring and an arc found within a few years of each other, and a claimed structure of 10 billion that is probably a mirage but has not been made to disappear. And sitting behind that list is the fact that every single time in the last 40 years that somebody said the structure was an artifact of a small sample, better data made the structure sharper instead. 47 million galaxies are now on the map. Euclid's first full cosmology release is arriving this month. Within a few years we'll know whether the ceiling is real, or whether the pattern goes further, and we simply had not drawn enough of it yet. Either way, the answer to the question we started with does not change. The universe looks less random the more we map it, because the randomness was only ever in the beginning, and the beginning is gone, consumed by a rule that had no choices in it. What we are looking at is not order that was placed in the universe, it is order that was left behind when the noise was used up. So the next time you see one of those images, the threads, the knots, the dark round hollows, the thing that looks so much like tissue that people cannot tell which is which, you can hold both halves of it at once. It was not designed. There was no plan, no template, no seed of the shape, nothing at the beginning but a smooth hot fog varying by 1 part in 100,000. And it came out looking like that anyway. 2 pictures nobody can tell apart, and now you know why.